Okay, we are recording now. Thanks, Utkarsh, for turning on the video. Guys, if a few more can turn on, that helps a lot. Thanks. Um, so we are into beamforming, and last class was non-trivial in the sense that we have to really understand, think about it a little bit to see what is going on. So I'll start this class. So the agenda for today is we are going to wrap up beamforming. Beamforming is a rabbit hole, okay? You can spend your whole life just doing this, okay? There are people who've just spent the last 30 years figuring out beamforming, angle of arrival, spatial filtering, signal processing. But what we're really doing is kind of skimming the surface and giving you the tools that would allow you, that would give you the courage to take on subsequent papers and problems or read more with these basic foundations. Otherwise, if you go into a paper, it will all look Greek and Latin. But of course, this is a topic which is, you need to think about it yourself a little bit to kind of see what is going on. So let me start. So what are we going to do today? So today we're going to finish up with beamforming and maybe for the first 15, 20 minutes, and then we are going to move on to a completely different topic, which is motion tracking. And we are going to start with some foundations of motion tracking using IMU sensors. IMU are inertial measurement units. So we're going to make a major gear change in today's lecture from Wi-Fi localization or broadly GPS and indoor localization. We are going to move on to motion sensing, motion tracking using mobile sensors such as IMUs. So today is a good day for you to kind of make sure that you've plugged the holes. If there's something that bugs you, something's not very clear, feel free to ask before we move on. So with that, let me start by saying any questions thus far from last class.
Could I ask a small question by voice?
Please.
Thanks. Last lecture, we said that if you increase the number antennas, your peak,
Right.
the peaks right above here that we see, they get sharper.
Yes.
I understand that. I kind of looked at the math and I convinced myself that that makes sense. Just wondering, I understand mathematically that the peaks go up. I was wondering if the side lobes also go down. Is there more? Because I understand with more antennas, there's more constructive action at the peaks. Is there more destructive action as well? Or is it just the peaks going up?
There is more destructive. Yes, yes. The side lobes also go down. Okay. The way to...
Why is that?
Yeah. Okay, let me quickly try to give you an intuition. Why don't I do this? Why don't I add a page over here? Yeah. John, that's a good question. And these are the kind of things that I want you to ponder upon. Okay. Basically, this is a topic that's like a gum that you can keep chewing and you'll get more and more juice out of it. Okay. So it's actually very interesting. So
that was me, by the way.
Oh, sorry. That was Lucas. Sorry.
You're good. You're good.
Thanks. So one way to think about this is the following. Every antenna is getting the signal with some phase shifts, right? And we know that every signal is essentially composed of a bunch of rotating sticks. So every signal sample that's arriving on an antenna, let's say that's this vector, that's this stick. That is an amplitude and a phase in the frequency domain, right? Now the signal sample that arrives at the adjacent antenna is another stick where this phase difference between the two is really that phi. So this is what is coming to antenna A0. This is what is coming to antenna A1. This is what is coming to antenna A2. and so on. Does that make sense? Lucas?
Yes, I'm following so far.
Right? So every signal sample that's coming to each antenna is like a vector, and these vectors are shifted by phi with relative to A0, 2 phi with relative to A0, 3 phi with relative to A0, and so forth. Right? Very good. Now, there is another signal that is coming, the second one, right? Which is, we said that there are D signals, right? So there are multiple signals coming. So the second signal that's coming, let's call, say, that one is this second signal, which is also coming to A0. And that one is shifted by some other phase. That depends on the angle of arrival. And let's say that other phase is psi. And so forth. If you've understood this, you're in great shape. What your antenna 0 is really getting is this signal plus this signal, these two. What your antenna 1 is getting is this signal plus this signal. Sorry. Your antenna 1 is getting this signal plus this signal. Your antenna 2 is getting this signal plus this signal. There's a bunch of vectors that are phi separated. There's another bunch of vectors that are psi separated. There's another bunch of vectors that are beta separated, each depending on the angle of arrival. So we can write over here that phi is, oops, what was that? My iPad sometimes have these issues. Phi is nothing but 2 pi by lambda d cos theta 1, where theta 1 is the angle of arrival of signal x1. Psi is 2 pi by lambda d cos theta 2, where theta 2 is AOA of signal x2. And so on till theta d, where theta d is AOA of signal xd. And you will have another one. Let's draw that one. Maybe there's another one which starts from here. This is antenna A0. And then this is antenna A1. And that separation is, let's call that beta. That's for signal XD. So now if you think of what your antenna A0 is getting, it's getting this signal plus this signal plus this signal. Those are all A0's signals. Okay. Now, when you're doing delay sum beamforming, you're essentially giving a phase shift. You're essentially trying to align all the black ones. Right? When you're giving a phase shift to each of your antenna with phi, 2 phi, 3 phi, 4 phi, so on, you're trying to bring this black, this vector to here, and this vector to here.
And this corresponds just to one, the black is just one signal, right?
One signal at, this vector corresponds to one signal at one antenna. That same signal is arriving at different antennas.
Okay.
Right? Just look at just think of the black signal. Let me redraw it again just for clarity. This one, this one, this one. This is coming at antenna A0, this is coming at antenna A1, this is coming at antenna A2, and so on. And let's say this is Bob speaking. This is Bob's signal. This is what Alexa hears from Bob at each of its antennas. Then there's some Susan also speaking simultaneously. The blue is Susan's voice coming to Alexa, starting with at antenna A0, this is Susan's voice. At antenna A1, this is Susan's voice. At antenna A2, it's Susan's voice, and so on. And if Susan's voice is coming from a different angle, then the antennas will see a phase shift, which is far shy, too shy, and so on. Right? By delay sum beamforming, what you're doing is you're saying, whatever phase shifts these antennas saw, I'm going to compensate for those phase shifts. So for antenna A0, you're saying I'm going to give it a phase shift 0. That means it stays there. For antenna A1, I'm going to give it a phase shift of negative phi. So this vector basically rotates and aligns with the A0 vector because you've given it a negative phi phase shift. Antenna A2, you give a negative 2 phi phase shift. So antenna A2 also aligns with this. So all the antenna signals, Bob's signal at all the other antennas are all getting rotated and aligned with the sig vector of the first antenna, of antenna A0 or microphone A0. So that's why they are adding up. But now look, this phase shift that you're giving of phi is also happening to all the other signals, Susan's signal on antenna A1, antenna A2, antenna A3. Those signals are also getting phase shifted, right? So when you're giving a phase shift to this vector and bringing it to coincide with this first black vector, this phase shift phi that you have given would also apply to this antenna A1, the second signal, which also get phase shifted to here by that same phi amount. Because you're giving the phase shift to everything that arrives at a given antenna. Guys? Lucas? Confusing?
Yes. I guess maybe I should let you keep going, but I'm just wondering, like, don't we see the side lobe decrease even with just one signal? Is it? I don't know if I'm just confused. I thought maybe it had to do with, you know, applying the wrong. We know it's the wrong shift, but because it's the wrong phase shift, they don't line up perfectly, and then they cancel. Maybe.
Oh, for other directions, your phase shift is wrong, right?
Right.
For the main looking direction, your phase shift is correct. For other directions, the phase shift is wrong. So more and more signals, more and more antennas you have, those wrong values start canceling each other. So more and more antennas you have, your side lobes will become smaller because
more cancel.
Those wrong values there are more and more wrong values, and that will start to cancel each other.
They sort of line up all around the circle.
All around it, exactly.
Okay. That helps. Thank you.
Right. And one way, and just to finish what I was saying over here is that once you align all the black ones with each other, the blue ones will get shifted by that phi, and the red ones will also get shifted by that phi, right? So if you have a lot of such black vectors and you're aligning all of them, the blue and the red vectors will also get shifted around by those phi. And more you have, again, that cancellation effect kicks in. The blue, red, green, yellow, orange, all of those vectors, or rather many of those blue vectors and many of those red vectors, they would all get moved around and they would cancel better if you have more antennas. Again, I think this is again something that needs pondering. Okay. Very good. Any other questions? Okay, if not, last class we talked about these delay sum beam forming and so forth. One point I want to make is the following. Let me just write this as questions. One point I want to make is okay. You remember when we said that here is an antenna and here is an antenna. This is antenna A0, this is antenna A1. This separation is D. This is theta. And this is D cos theta. You remember this, right? And we said that the phase difference between A0 and A1, is phi, which is 2 pi by lambda d cos theta. You remember that, right? That was the phase difference between the two signals, because we said, look, in far field, this length and this length is the same. So this signal travels a d cos theta distance more, and that d cos theta distance translates to phi phase. Okay. Now we divided this by 2 pi by lambda. What does that mean? That means this signal has only one lambda. Means the signal has only one frequency. Right? We assumed that signal has only one frequency, therefore only one lambda. So this is true, this is correct when the is what is called narrowband. If you record my voice, like if I say tee, and you record that, right, it will almost have only one frequency. Actually, it will have some other frequencies, but you can generate a signal which has only one frequency, and it's often called a tone, and the tone will sound like tee. If you increase the frequency of the tone, it'll tee, it'll sound like that. Beep, right? These beeps often have very low frequency, very small frequency band. So these are often called narrowband signals or tones. So everything we did thus far is actually for tones, because that tones help us think of the problem in a simplified way, because we can say, look, the phi phase difference is 2 pi by lambda d cos theta. But if you now imagine that actually the transmitter over here, for whom we are trying to do AOA, is actually a human, or is actually a Wi-Fi signal. or a millimeter wave 5G signal, right? All these real signals, they have a wide bandwidth. Now we are going back to our Fourier understanding. Real signals, real world signals have wider bandwidth. How much is human voice? How much is the bandwidth for human voice? Someone?
20
0 to 20,000
kilohertz. Although most of the human voice is contained within 8 kilohertz, but there is some energy in the 20th kilohertz. Wi-Fi, someone? Anyone? What is the bandwidth of a Wi-Fi signal? 20 megahertz. Okay. What are we thinking about 5G? What kind of bandwidth can we do in 5G? People are talking about 500 megahertz. These are called ultra wideband. Okay. So now if I tell you, okay, guys, your cell tower is transmitting a Wi-Fi signal, or your Alexa says, okay, Bob is saying, hi, Alexa. What is the phase difference between two antennas? Your answer should be, hey, there's no single phase difference. Every frequency will have a phase difference. Right? Because this lambda will now become, in this situation, this lambda phi I, or let's call it phi fi, will be 2 pi by lambda for that corresponding frequency times d cos theta. Right? So now you have to treat signals differently. If you can only have one phase, right? You only have one phase by which you can move the signals, as we were doing over here. We were moving the signals by this phi. And suppose you have only one such phi that you can control at the antenna. The question is, which phi should you pick? If you pick for some one lambda, for the other lambda, that phi won't work. Right? So then it can become an optimization problem that you can say, okay, look, I'm going to pick phi for that frequency which has the most amount of energy. Does that make sense? Suppose my voice, if I take an FFT of my voice, suppose the FFT of the voice, this is 20 kilohertz. Remember, this is the FFT spectrum I'm talking about. And my voice, it looks like this. Actually, human voice has this nice property of what is called harmonics, meaning there is a base frequency and there are other frequencies that are integer multiples of that base frequency. A male's base frequency is less than 200 hertz. A female's base frequency is less than 400 hertz. So female base frequencies are typically higher than male base frequency, right? That's why male bases are more like bass sounding. Females have a higher base frequency. Right? That's the higher frequency. So this is what the human spectrogram will look like. And now if I say, how are you going to do phase if you have only one measure, one value that you can turn at your antenna? You can change your antenna signal, give a phase shift with only one phase phi. Maybe the best thing to do is to use the lambda corresponding to this frequency. Right? Because that frequency has the highest energy. And so you optimize for that, and maybe these frequencies, even though they will have the wrong phase, the vectors will not line up perfectly. Maybe that's okay. That's the problem you live with. As long as you optimize for the highest energy frequency, you're fine. That's the best you can do in some sense. Right? Does that make sense? So I want you to remember that what we did thus far, all the understanding that we have thus far is for a narrow band signal. For wideband signals, we need to do other things and we have to be more careful. Questions? Okay, good. So that is what we are going to talk about delay sum beamforming and angle of arrival estimation. And you know, these things do not work very well with multiple users or with few users that are close to each other for reasons we talked about, where we said, look, when there are two users, their AOAs are like that, you add them up and you get a very blunt peak, and that blunt peak is at the wrong location because you're adding up these two AOA spectrums. Very good. So I want to now tell you that there are other techniques, okay, other than this core notion of lining things up. Right? That's one way to say that I am going to give different phase shifts to these vectors, and then I'm going to see at which phase shift the AOA spectrum has a peak. Guys, is this intuition clear that the AOA algorithm is essentially taking each of these antennas and giving them phase shifts? First, it starts with 1 degree phase shifts. So it takes these antennas, it gives this phase, the first antenna, it gives a 0 phase shift. The next one, it gives a 1. The next one, it gives a 2. And next one, it gives a 3. And it sees how well the signals line up, meaning how much is the net signal after adding up all of those antenna signals with those phase shifts. And you say, okay, that didn't add up too much. Then what do? You take those same 4 antennas, you give this 0, then you give this 2, 4, 6. You again add up. And you see how much the result is. You say, oh, again, it's not good. It's still pretty small. Then you keep doing this, and at some point you give 0, 30, 60, 90. And then you see, whoa, things just spike up. Why? Oh, because when the signals arrived at these antennas, they were actually minus 30, minus 60, minus 90 phase shifted because of that d cos theta. And now because you've compensated for those delays, your signals all line up and they spike up. Right? So then you say, this is the right phase shift. And you could calculate the theta corresponding to this phi. And you say, that's my angle of arrival. Right? That's the core idea with delay sum beamforming. Right? We've just made things get complicated when there are multiple signals, but the core idea is correlation. Okay? And that is what we were saying over here. The received signal is different AOA directions multiplied by each of the source signals. This multiplication is nothing but x1 times a1. A1 is one particular direction from which the signal is coming, plus x2 times a2, so on xd times ad. And what you're trying to do is you're multiplying with different values of AI with your received signal, which is the same as multiplying with this AI with this matrix multiplication. And when this AI and this AI matches up, all the vectors get aligned. And when this AI and this AJ does not match up, the vectors are all over the place, so you don't see that coherent constructive alignment. And that's what gives you the AOA spectrum. Okay, please do ponder around it and go back and think about it. This is one approach of delay summing, and there are many variations of it. Now, today we are going to quickly talk about another approach. This is mostly talked about in grad level courses, but I just want to give you a sense that antenna beamforming AOA research has gone far And there are other techniques, other completely different kinds of techniques that exist. And it's good to know that they exist, even if you do not fully understand what's going on. Okay, very good. The signal that you receive at your antenna vector is Y, and that can be modeled as AS plus N. Please tell me if you understand this equation quite well now, or if you don't understand this equation. This is the same thing we just saw. Y is nothing but Y0, Y1, Yn minus 1. What is Y0, guys? Y0 is the, can you fill in the sentence? What is Y0?
Received signal at antenna 0.
Perfect. Okay, that's Y, it's Y0, Y1. So this is what your antenna array is receiving. A is A1, A2, so on. Let's keep it 3 values. Let's keep it 3, yes, just for simplicity. A3, X1, X2, X3. What is A, guys? What is this matrix A in English language?
It's quickly. Like go ahead,
Lucas.
It's like the delay associated with that specific path.
Correct. This is the set of delays associated with that specific angle of arrival. This, the second one, is the delays associated with the second angle of arrival for the second signal. This is the delay associated for X3. This is obviously a vector which is of the form n cross 1, right? When you multiply these two, I always want you to think of matrix multiplication as x1 times this column plus x2 times this column plus x3 times this column. Okay. Plus this whole thing plus the noise sequence n0, n1, and n minus 1. Right? Noise is getting added at the received antenna. So this is the Y equals AS plus N. You should always think of it this way. And this is called the steering matrix, like we said. And X is the source signal, N is the noise, Y is the received signal. Very good. Now, imagine, now let's look at this. If you have this equation, we can always make it Y times Y Hermitian. Hermitian is nothing but conjugate transpose. Okay, so you take that matrix, you conjugate it, E equals e to the power j theta, you make it e to the power minus j theta. That's conjugate. And the column becomes a row. Okay, this is typically what is called covariance or correlation. This is basically correlation. You're taking a vector and you're multiplying it with the conjugate transpose of that vector. So YYH should be AS plus N times AS plus NH. H is nothing but conjugate, or we can write this as Y conjugate transpose. Okay. So right hand side also has that Hermitian. When you take random processes later, you will realize that this is what is called autocorrelation. It basically tries to understand what is the similarity or the difference between the signals and between the signal that you get and the next time step of the signal that you get and the next time step of the signal that you get. What is the similarity between them? That's what this correlation matrix captures. But you don't have to get into that detail. You just need to see that if I do this operation on my left-hand side, I should do the same operation on my right-hand side. And this operation Basically, physically, it means that I'm trying to understand the correlation, the similarities and dissimilarities between the signals that are coming to the antenna. Very good. So then I can write the right-hand side as AS plus N. And remember, A times S, when you take the transpose of it, it becomes S transpose A transpose. Right? AX transpose is X transpose A transpose. You know that, right? So this becomes S Hermitian A Hermitian plus N Hermitian. Now multiply. This becomes AS S Hermitian A Hermitian, AS N Hermitian, this times this, N S Hermitian A Hermitian plus N times N Hermitian. Okay, very good. Now, this signal that you've gotten is at one timestamp. It's at one snapshot, right? Now you can get multiple snapshots and you can make this vector a matrix where the first column is the time t1, second column is time t2, third column is time t3, and so on. And you can similarly do that for the right-hand side. x1, x2, x3 is the first sample that the 3 users send. The next column of that source signal matrix will be the next set of samples, and so on. So instead of having a vector on both sides, you can make it a matrix on both sides. Guys, is that clear? Correct. So in some sense, I'm adding a time to each of these. So now if it's a matrix, I can take expectation, and that expectation of this is going to be the expectation of this whole thing. Okay, very good. Now, again, if you do not understand this fully, you're fine, but just stay with it. So let's call this expectation of the similarity properties of the signal that's coming over time. That is nothing but expectation of this is A, expectation of the similarities or dissimilarities of the source signal times AH. This is expectation of the noise and the source signal. So it's essentially saying, is the noise and the source signal on average similar, correlated, uncorrelated? And typically, we assume that the noise and the signal that you are speaking, or the Wi-Fi signal that is coming, they're uncorrelated. Does that make sense? Right? There's no reason why the sound that is coming out of your mouth and noise, which is random, should have similarity, meaning that they'll go up and down at the same time. There's no reason to believe that. In fact, there's completely no correlation in expectation. So source signal and noise is uncorrelated. Similarly, conjugate of source signal and noise is uncorrelated. So these are both 0. And this is noise correlated with noise, which is the power of the noise. Okay. Noise correlated with noise gives you the power of the noise. Okay. So this gives, this gives you the power, and that power times identity matrix. If you're worried about that, think of it this way: N1, N2, N3, so on. Okay, maybe I won't go over there. If you're not clear about this, talk to me at the end of the class. Okay, but this is an identity matrix multiplied by sigma square, where sigma is the power of the noise. Okay. Good.
Professor?
Yes.
Y times Y, Y times Y Hermitian is like the correlation between antennas, right?
Correlation between the signals that are received at these antennas.
Okay, but not like time. I understand we added time at like, I understand the time part, but that's not time, right? That's correlation between antennas, not time, right?
Right, right.
Okay, okay, thank you. Yeah, signals received. Okay, thank you.
Across the time, yes. Okay, so look, this is a M cross M matrix. You agree? Y is, let's say M microphones. We have M microphones and we have D signals. Guys, does that make sense? So this is an M cross M matrix. Y is the M dimensional vector, Y Hermitian, right? It's an M cross M matrix. The rank of this matrix is M. Okay. Very good. What dimension is this matrix? What is A? What is the dimension of A? Someone from here?
MXD.
M times D. Very good. What is RSS? What is the dimension of that matrix?
Is it just a scalar?
No, wait. X, the X, this is X1, X2, X3 at time 1. Then there is X1, X2, X3 at time 2.
Is it D by D?
It's D by D. Okay. So let's say there are only 2 timestamps that we are taking. Then this S Hermitian would be X1, X2, X3 at time 1, X1, X2, X3 at time 2. I hope you see this. So it's D by D, right? Right. This is 3 cross 2. This is 2 cross 3. Therefore, it's D by D. 3 cross 3. Maybe I should put it up there. Where should I put it? Maybe I should put it up here. So this is D by D. And what is AH? What is AH?
D by M.
D by M. Very good. It has to match the left-hand side, which is M by M, and this matches the left-hand side. Plus 0 doesn't matter. And what should this matrix be? This matrix I is M cross M. And it's multiplied by a scalar, which is sigma square. And this matrix is rank how much? Matrix I of M cross M is what rank?
M.
M. Very good. Now, this matrix, the rank of this matrix A, RSS, AH is how much? let me say one thing. The rank of a product of matrices AB, anyone knows? Did we talk about this in the homework? The rank of a product of matrices AB, can you express that as, if I give you the rank of A and I give you the rank of B, can you tell me what is the rank of product AB?
Was it at most the minimum of the
Perfect.
two matrices?
Exactly. So this is minimum, or yeah, at most minimum of rank A, comma rank B. Okay. Now tell me what is the rank of this matrix? A, RSS, AH. What is the rank of A? Let's say M is greater than D.
The whole thing is rank D.
Whole thing is rank D. Okay. Whole thing is rank D. Very good. So now look, what do we have? Now this is where the intuition comes in. We have the left-hand side is a matrix of rank M. That means it spans an M-dimensional space. Right? This one, this matrix is essentially the source signals mixed by the steering matrices. And that covers a D-dimensional space, which is a subspace of M dimensions, because at D is less than M. Right? So this means that the signals, the source signals, Bob is saying something, Susan is saying something, Alice is saying something to Alexa. And when the source signals come, the source signals are mixed up at the antennas. But the source signals span a D-dimensional space because there are D sources. But because I have M antennas, I have mixed those signals, mixed those D vectors and spanned M-dimensional space where M is greater than D. It's kind of, I have done an inflation. Make sense? And there is noise which is spanning M-dimensional space. Make sense? Does the intuition make sense? That look, you have D signals, that D signals, even if you take the covariance of them, it's going to span D-dimensional space. But what I've received with M antennas is M-dimensional signals. So that means somewhere that inflation must have happened. Right? So now imagine this matrix, you bring this to the left, Rxx minus sigma square I. Rxx minus sigma square I must be a D-dimensional matrix, right? Sorry, must be a rank D, must have rank D. It will not be a D-dimensional matrix. Rxx minus sigma square I is still an M cross M matrix. Because this is M cross M, this is M cross M. You subtract two matrices of M cross M matrix, it will be an M cross M matrix. But its rank has to be D. Why does its rank has to be D? Someone? Utkarsh? Why does this rank have to be D?
Because it equals A, RSS, AH, which
exactly.
is D.
Because it equals this. If this rank is D, this rank has to be D. Oh, that means what did it tell me? It tells me that if you think of this M-dimensional space for Rxx, when you're subtracting noise, you've made it D-dimensional. Sorry, you've made it D-dimensional, right? That means in this in this matrix, there is a d-dimensional subspace in which the signal lies, and the rest of it is the noise subspace. M minus D is where the noise lies, because when I brought in the noise, that m-dimensional rank went to d-dimensional. So in m-dimensional space, the signal was scattered, but when I brought in the noise, the signal actually, the noise subtracts it. And the signal now is in d dimensions and the rest of it is noise. M minus d dimensions. Now, if you calculate the eigen decomposition of this matrix, right? This is rank D, but the matrix has m eigenvectors. So m minus d eigenvalues would be 0 because it is rank D. Suppose m is 10, d is 5. Oh, okay, let's say d is 4. That means for this m cross m matrix, you are going to get 6 eigenvalues that are 0. Right? But if you think of that m cross m space, there are m eigenvectors, right? You can come up with a 10 cross 10 basis. Remember, we said that we can always do eigen decomposition and we can come up with a m cross m basis. So out of those 10, 6 eigenvectors, right? This matrix times the eigenvector is lambda times the eigenvector. This lambda is 0 for 6 of them. So that means there are 6 eigenvectors for which the lambda is 0. The eigenvalue is 0. Those 6 eigenvectors, right? Those m minus d eigenvectors, when you multiply on the right side, they should also give you 0 because this is 0. If this matrix times some eigenvector, which are those 6 eigenvectors, gives you 0, then the right-hand side multiplied by those eigenvectors should also give you 0. I know it's getting hard, but maybe in 1 minute, maybe we'll get some intuitive clarity. But think about that this matrix has some eigenvector, which when that matrix times the eigenvector, ax equals lambda x, that's our eigenvector equation. This a with this x equals 0 times x. So this 0 is the eigenvalue. That means this must be an eigenvector that takes it to 0. Which means this eigenvector must also take the right-hand side matrix to 0, because if you multiply the left-hand side with this eigenvector, the right-hand side will also be multiplied by that eigenvector. Now, if this right-hand side has to be 0, now observe that A and AH are both, A and RSS are both full rank. A is a matrix, this matrix. You can prove that this A matrix is full rank because as long as signals are coming from different directions, all these columns will be linearly independent. There's a proof that says the delays that happen from different angles, they're always linearly independent. This is called a Vandermonde property. So A is full rank. If A is full rank, A times this eigenvector cannot give you 0. RSS, we are going to assume it's full rank, meaning the source signals, Bob's speech and Susan's speech and Alice's speech, we are going to assume they are uncorrelated. So this is also full rank. So this idea would only work when the source signals are uncorrelated. So if these two are full rank, this eigenvector multiplied with these cannot be 0. Because look, if these two are full rank, there should be no vector that multiplies these two to take it to 0. It shouldn't have a null space, which means AH must be a matrix that has this eigenvector in its null space. Okay, I know this is difficult, but here is how to bring it together. We are saying that if I take the eigen decomposition of the correlation matrix that we have received Y, we can get its correlation, autocorrelation matrix. That autocorrelation matrix, if we do an eigen decomposition of it, it will separate out into a D subspace which has the signals in it, and a M minus D subspace which has the noise in it. And these are orthogonal, right? Because we know that this is a M dimensional subspace, but it's rank D, and these are the M minus D are orthogonal. So we are going to say that, and from that we see that the directions that are orthogonal are also orthogonal to AH, which is the steering matrices vectors. In other words, some of the eigenvectors of my received signal autocorrelation should be orthogonal to the directions in which the actual signals came. Let me say that again. Some of the eigenvectors of the received correlation matrix or of my received signal is orthogonal to the actual directions in which the signal came. I can calculate the eigenvectors of my received correlation matrix, and I can take that eigenvector and I can check which directions is orthogonal to those eigenvectors, and whichever direction is orthogonal to those eigenvectors, I'll say that is the direction in which the signal is coming. So my AOA spectrum now is 1 divided by A theta I H, meaning I'm going to try for different angles of arrival and multiply with those eigenvectors. I know these eigenvectors from eigen decomposition of my received signal. Whenever, and I'm going to try different angles, whichever angle is correct, that angle's delays, that A vector should have a dot product of 0 with my eigenvector, and therefore this value should become 0, and 1 by that 0 will spike up, ideally infinity, and I should see an AOA spectrum like that. I know this is difficult, okay? I know it takes a lot of time to get it, but all I want to say is here is another, the least you should understand is there is another way of approaching the AOA problem, right? I'm sure that all of you have understood. The second thing that you should understand is it has something to do with eigen decomposition. I hope that also you've understood. The third harder thing that you need to understand is whatever signal I'm getting at my M antennas, that creates an M dimensional space. But because M is greater than D, where D is the number of signals that are coming in, that M dimensional space is composed of a D dimensional subspace and an m minus d dimensional noise space. Okay, that also I think you intuitively get. Now it turns out, now this is the part which is hard to understand, is the basis for that noise space, the basis for that m minus d dimensional noise space, those basis vectors turn out to be orthogonal to the steering matrix vectors of the signal, to the directions in which the signals are coming. To those directions, these noise space vectors prove to be orthogonal, and the math says so. So therefore, we now have a way to check if the direction that we are testing for is correct or not. How do we check? We get the basis for the noise subspace, and we multiply and we see if they are orthogonal or not. If they're orthogonal, we know we got the right AOA vector. Okay. That's the high level takeaway. Okay. Again, if you've understood that much, good enough. Okay. So now let's bring all of this to a practical system. Let's go back to indoor localization with Wi-Fi. These are your Wi-Fi routers, Wi-Fi AP1, AP2. And your phone transmits a beacon. And your Wi-Fi router 1 does AOA and figures out, oh, the beacon is coming from angle θ1. The AP2 says, oh, I see, the beacon is coming from angle θ2. And assuming that you know the locations of the two Wi-Fi access points, then you can say, oh, this is θ1, that is θ2, where do they intersect? And from that, you estimate the location of the phone. Does that make sense? Right? This is called triangulation. But of course, you need to know the location of the Wi-Fi access points. And you can apply delay sum over here. You can apply, by the way, this algorithm that we talked about is called music. It's very popular. So you can apply delay sum, you can apply music, you can apply whatever you want. Okay. Once you get the AOA, you can do triangulation by just solving that problem. Okay. What happens with multipath? Right? Of course, this signal is not going to go directly. The signal is not going to go directly. There's going to be reflections that will also go. So what happens then? The LOS, the line of sight path varies. Okay, let me ask this question. This signal is going to come in through here because there's a reflector here. This signal is going to reflect in other places and come in like that. There's a reflector here and so on. So your AOA spectrum will have multiple spikes. Right? Your AOA spectrum will now look like that. These are all the multipath. From this, how will you say which one is the line of sight path, which one is the multipath? Remember that if you for triangulation, if you use a multipath for triangulation, you're completely going to be wrong. You see that? Guys, I hope I haven't lost you with music. Even if you didn't understand music, just forget it. Right? Now we are doing triangulation where the Wi-Fi AP has figured out the AOA of the phone. The question now I'm asking is, suppose the AOA, you also have figured out the AOA of the reflections, of the echoes. So now from your AOA spectrum, if you use the wrong AOA, your triangulation will completely get derailed. So the question I'm now asking you is, your AOA spectrum tells you this. Forget how you got it, whether you got it by music or delay sum, doesn't matter. You got this. And now you want to do triangulation. Which theta are you going to pick? Let's say this is theta 1, this is theta 2, this is theta 3, this is theta 4. Which one are you going to pick? If you pick the wrong one, your localization will be completely wrong. How will you pick the right theta? The LOS, the line of sight theta.
Can you use power maybe?
Using power might be an idea, but there might be some walls over here, and your received signal along the line of sight path might actually be weak. So your power may not be necessarily, the line of sight power may not be stronger necessarily. Maybe it will work as a heuristic, but not necessarily. What else? Any other ideas? Let me try to give you a hint.
A statistics thing or?
Statistics, like what kind of statistics?
Try to find the one that's not an outlier, I guess. Like if you have a bunch of like results and they're all like, if they all fall into like a median, I guess, maybe try to get the median. I'm not sure.
Sure. But this is the thinking in maybe the right direction, but let me quickly give you the answer. Let's say the mobile phone is moving. Okay. So at time t1, you get this AOA spectrum. At the next time, what kind of AOA spectrum do you think you're going to get? The intuition is that as you move, can you tell me what do you expect for the line of sight angle and the multipath angle? Can you say anything? Can you think of what happens to the line of sight angle and to the multipath angle as you move?
Line of sight should stay in the same absolute relative, like absolute direction, and then the other one should change.
The multipath is more likely to change. Lucas, you're right. Why? Because the reflectors are all over the place. So you will get a new reflection because your incident angle is changing. Some object, you might have crossed some object, so that multipath will disappear. There's going to be a lot more fluctuation in your multipath as you're moving, but your line of sight angle should change slowly. So the next time you're going to see something like, if let's say this is the line of sight path, then the next time the line of sight path will change a little bit, but the other multipath would change more. Right? So as you take multiple snapshots, you will see stability in one theta and the other theta should show fluctuations. Right? There's a chair. The moment you move a little, the chair's reflection is no longer there. That multipath goes, that AOA goes away. But the line of sight path remains relatively stable. So you look at this time sequence, hoping that the user is moving, and from that you pull out the stable AOA, and you use that for triangulation. Okay? So let's write that out. Line of sight path varies slowly, while multipath varies faster, or multipath AOA, line of sight path AOA, very slowly. Okay. So identify line of sight by observing stable AOA spectrum peak, and then you apply maximum likelihood estimation, MLE for localization. If you're not familiar with maximum likelihood estimation, it's not that hard. All you say is you pretend, by the way, guys, those of you who are not comfortable with maximum likelihood, it's one of the easiest thing to understand. Whatever you're trying to estimate, just pretend you know that. Okay. So you're trying to estimate the location of this phone. Pretend you know that the location is at some location x1, y1. And then you compute the probability. If this phone was at x1, y1, what is the angle of arrival that I should have seen at my two Wi-Fi APs? And if you're going to see, if you should have seen θ1 and θ2, you say, okay, if I should have seen θ1 over here, what is that probability? You look at θ1 and you take the AOA spectrum value over there. Right? So you pretend that you know the phone's location, but you pretend that the phone is at x1, y1, x2, y2, x3, y3, x4, y4, at all locations. And for every location, you compute the probability. If I was this, if the phone was at x1, y1, what should have been the probability? In other words, if the phone was at x1, y1, the angle of arrival should have been 35 degrees and 75 degrees. Let me go and check with Wi-Fi 1, AP1, that if this was 35 degrees, what is the probability? That is like saying, go to the AOA spectrum and ask 35 degrees, what is the probability? And maybe the AOA spectrum is very low for 35 degrees. Then you say the probability is low. Right? When you get the right location for the phone, you will have the right angles and that probability will be higher. And thereby, you will figure out that that's the right location because those probabilities will get multiplied and will be much higher. Okay? So that is how you basically do triangulation. And there's a paper called ArrayTrack that is on your website that is for review. It's an interesting paper and I would like you to read that paper. And if you understand this reasonably well, ArrayTrack uses music. So you get a first encounter with music. If you don't understand fully, that's fine. But it's a good way to understand what kind of research happens in these kind of localization with triangulation, with beamforming and so forth. So if these things roughly interest you, there's a lot of work you can do along these dimensions. Okay, that's all we'll say about, I started off saying 20 minutes. Any questions thus far? I know this was a heavy class. But ArrayTrack might help. And if you're interested, I might actually even post some more watered down version of music that you should be able to follow. And again, we are not going to test you on any of this in the midterm where, oh, come with some derivation of music or tell me more around music. But if you understand the intuitions of what is going on, what are these two spaces of signals and noise, I think that itself is helpful. Okay, if there are no questions in the last 5 minutes, I want to get started with the other topic and then we'll continue next class. And the other topic is, like I said, it's a big gear shift into inertial motion tracking using IMUs. Okay. And the new topic we'll talk about is essentially around the following. We want to track motions, let's say of a smartwatch on a person's wrist. And as the person's moving her wrist, we want to understand how the wrist is moving by looking at sensors from the watch. That's one application. Okay. Another application might be you're wearing a VR goggles. That goggles has a motion sensor. You're looking through VR. You're looking at different directions in VR. And I want to understand how your head is moving. Another application could be, you know, drones, right? When they fly. Okay, let me ask you this. Drones have motion sensors in them. Why? A motion sensor often is an IMU. The most popular motion sensor is an IMU. The IMU, which is called the inertial measurement unit, here, is made up of an accelerometer, a gyroscope, and a magnetometer. We'll talk about them. But accelerometer basically measures acceleration, gyroscope measures angular velocity, and magnetometer measures the Earth's magnetic field. And a drone has an IMU in it. Why on earth does a drone need an IMU? Can someone tell me? The drones also have GPSs on them. So why does a drone need an IMU? Any ideas? Any random guesses?
Is it stabilizing the different rotors?
Correct. Lucas, can you say anything more? Why does it need to stabilize? Can you explain?
Maybe I'm just thinking like maybe there's some wind on one side more than the other side. And if you just keep rotating all the rotors the same, you'll just flip over probably.
Nice. No, that's exactly the right intuition. Okay? But I can make it simpler. A drone is flying. When a drone flies, all the rotors are spinning at the same frequency, at the same speed. When the drone now wants to take a turn, what happens? The inner rotors slow down, right? Let's say I'm going to take a left turn. The inner rotors slow down and the outer rotors speed up, right? So the drone is taking a turn, speed up, and again the drone stabilizes. Again, the rotors become equal, the speed. So so now if you think of the drone's controller, it needs to know how much it has bent, how much it has turned, and once it has turned fully, the rotor speed needs to be changed again, right? So it needs to understand how much it has turned so that it can control the rotor speeds. This motion needs to come from the IMU. Okay. Another application, there are startups. In fact, we also did work on this, where you put a motion sensor in a baseball or a cricket ball or a basketball, and now you throw the ball or you pitch the ball, or in cricket you do a bowling. And once you do that, if you can understand exactly how the ball moved, you can do all kinds of analytics. Right? In fact, if you think of coaching, someone throws a curveball in baseball, and you can immediately read from your phone exactly how the ball moved. If the ball has a motion sensor that tells your mobile phone, oh, this is how I moved. Robots, self-driving cars, all kinds of applications, satellites, all kinds of applications. Planes, ships. So motion tracking is very popular, and IMUs have been super integrated in many, many devices. So there's wide applications in motion tracking for these IMUs. Okay. So the core algorithmic problem that you and I are interested in, and many, many industries are interested in, is the following. You want to develop a motion tracking algorithm. This is your goal, whose input is the IMU data from accelerometer, gyroscope, and magnetometer. And your output should be the 3D trajectory of that sensor. And that sensor might be in a phone. In that case, you're tracking the phone. That sensor might be in a ball. In that case, you're tracking the ball. The sensor could be in a drone. The sensor could be in a ship. The sensor could be in a satellite. Doesn't matter. Wherever the sensor is, you're tracking the motion of that sensor, of that chip. That's your goal. You need to come up with this algorithm. Let me tell you, if you solve this problem, you will be very quickly a candidate for Nobel Prize. If you can precisely solve this trajectory of the IMU from the IMU data alone. Okay? So this is an open problem in mobile computing. No one has the solution. People are making progress. It's hard. Okay? So let's understand what's the real difficulty here. Yeah, I will formulate the problem, and we'll talk about the solutions next class. Okay? So let's understand what is this, why is this problem so hard, right? Because ultimately we want to develop this algorithm. Great. So we need to have one prerequisite for this, for understanding this problem. And that prerequisite again goes back to linear algebra. Okay. And that prerequisite is rotation matrices. Remember when we said AX equals B, one way of looking at that is, I don't know how to delete. Okay, I'm going to delete like this now. One way of thinking of AX equals B is X is a vector that goes into a function A or an operation A and comes out as B. So think of A as an operator or function on X. Can you think of it that way? You have a vector X, I multiplied with A, that vector X becomes B. Okay. So if you think of it that way, then I can also think of matrices A that takes a vector X, rotates it, and creates another vector B. So then A, which is a matrix, can be a rotation matrix. So for example, I take this vector and this vector, and if I multiply it with some matrix, I can make the green vector go here and the blue vector come here. I rotate it with 90 degrees counterclockwise. I can create matrices like that. Here is an example. If you take this matrix and if you multiply it with this matrix, you will get this. And this matrix is nothing but a 90 degrees rotation. So AX equals B. B is 90 degree rotation of X. Are you comfortable with that? A matrix, if it has certain properties, it can be a rotation matrix. Here is one I gave you right now. Any questions thus far? Not all matrices are rotation matrices, obviously, right? But special matrices, I can design matrices. If I tell you design a matrix that will rotate a vector 45 degrees, you can easily design such a matrix. Easily. Here I gave you a matrix that rotates 90 degrees counterclockwise. Okay. Now, if you're comfortable with this, you can take one more step in your imagination that we can now do this for 3D as well. I can take a 3D basis, I can multiply with that some 3x3 rotation matrix, and that whole basis will change. Right? I can make this into this, where there's a rotation, and I'll do that by multiplying it with this matrix. Bottom line, rotation of vectors can be modeled as matrix multiplication, as long as you get the right matrix. Clean? That's all you need. One slide prerequisite for IMU tracking. Great. With that, now let's look at the problem formulation. You need to design this algorithm. Your inputs are twofold. This is the problem, the one that will get you the Nobel Prize. You are given two inputs. One input is the IMU data from the accelerometer, gyroscope, and magnetometer. And also, I will give you the initial location of that IMU. Okay, so imagine a plane. A plane has an IMU on it. I will tell you that the plane is at Chicago Airport on the runway. Okay, that's the initial location. And from now on, I will give you the plane's IMU measurements. Okay. Your goal is to design an algorithm, and the algorithm will output the plane's trajectory on the global map, on America's map. You have to tell me the plane is going to give you data from the IMU. You have to say the plane is taken off from Chicago. It's exactly on Lake Michigan right now. It's exactly taken a turn on Arlington Heights around Chicago. Now it's going over the downtown Chicago. You have to tell me the plane's trajectory on the Earth's map. It's as simple as that. Okay. Initial location, I can say that as X0, Y0, Z0. That's the initial location of the plane. And the IMU data is accelerometer, gyroscope, magnetometer. Let's understand the inputs quickly. What is this accelerometer, gyroscope, magnetometer? Accelerometer, as I said, measures acceleration. It gives you a vector at every time instant. As you sample the accelerometer, typically the sampling rate of an accelerometer is 200 Hertz. It'll give you data 200 times in a second. And every data will be a three-dimensional vector, meaning giving AX, AY, and AZ, where AX is the acceleration of the IMU along IMU's X direction. Okay, so if you think of a IMU, this is the IMU chip. It has an X direction, it has a Y direction, and it has a Z direction which is coming out of the paper. Okay, and as the IMU moves, it gives you the X, Y, Z directions acceleration. So if this IMU is in a phone, like this, say this IMU is in a phone, it is actually like this. So the phone's short end is the x-axis, the phone's long end is the y-axis, and the direction coming out of the phone is the z-axis. Guys, is this clear thus far? So accelerometer is giving you the phone's acceleration in its own X, Y, and Z directions. Very good. The gyroscope data also gives you a three-dimensional vector, Gx, Gy, Gz, which says the angular velocity of the IMU around the x-axis. Right? So if I take this phone, this is the x-axis, right? IMU is x-axis. So if I rotate this x-axis, the phone would rotate like this, right? That is the angular velocity Gx. This is the y-axis. If I rotate the y-axis, then the phone would rotate like that. Sorry. That is Gy. And if I rotate, this is Z. If I rotate this one, the phone would rotate like that. That is Gz. So this gives me, gyroscope gives me these three values at every instant. d theta by dt along x-axis, around x-axis. Finally, magnetometer is basically measuring the Earth's magnetic field. Earth is somewhere, Earth has a magnet like that. That's north. So your phone looks at this 3D vector towards the Earth's magnetic field. And what mx, my, mz gives you is the projection of this 3D magnetic field towards x-axis, y-axis, and z-axis. This is the magnetic field M projected to x-axis, that gives you mx, projected to y-axis gives you my, projected to z-axis gives you mz. Earth's magnetic field projected to x, y, z axis. Guys, is that clear? Very good. Once you have this input and the initial location, your goal is to continuously estimate xt, yt, zt, because that's the location of the object of the IMU as it's moving. This is the formulation of the problem. So one can say, that's not hard at all. It seems very simple. Why is it simple? What can you do? So this is what I'll do. I know the initial location. I also know that double integration of acceleration gives me displacement. Right? Single integration of acceleration gives me what? Single integration of acceleration gives me
velocity.
Velocity. And single integration of velocity gives me displacement. And displacement is a vector. So I can double integrate acceleration, I'll get displacement. That's my displacement from my initial location x0, y0, z0. Voila, I have my solution xt, yt, zt. So as I get the accelerometer values, I will keep double integrating and I'll get the displacement. I can continuously track this object. Does this idea make sense? Okay. Anyone, why does it not work? This is one huge problem. Remember I said, maybe quickly, this acceleration ax is with respect to the IMU's own x-axis, right? But your job is to say, where is the plane? Where is the plane on Earth's map? So here is the problem. Let's take an analogy. Your friend is on the flight, okay? And your friend has called you. And your friend says, you know what? I am at gate number 33 at O'Hare, Chicago O'Hare Airport. That's my initial location. And I will constantly read out my IMU data to you. Can you track where I am going on the Earth's map? That's the problem. You say, okay, I'm ready. I'm going to do double integration on the acceleration data that you're going to tell me. Okay, so your friend says, I am at gate number 33. So you exactly know where gate number 33 is in Chicago. That's your initial location. And your friend starts. AX is his own x-axis. Maybe that's forwards. He says, I am experiencing 5 meters per second square acceleration in my x-axis. What's your question? Can you solve your, can you say where your friend is going on the airport, how the plane is moving? Thoughts?
You need to know where he's pointing, right? Because
you need to know where he's pointing. In other words, you need to know how his phone is oriented with respect to the Earth's map. Right? In other words, if your friend says, I'm going towards X and Y and Z, which is like, let's say, frontwards, rightwards, upwards for him, what does it mean with respect to Earth? What is your X, Y, Z with respect to Earth? The phone, if the phone is oriented like this, then the phone's X is this way, which is maybe east. The phone's Y is north. The phone's Z is towards the sky. But if the phone is oriented this way, because the plane is actually pointed that way, then the phone's X is this, which is some southwest. The phone's Y is this, which is some southeast. And the phone's Z is still sky. If you do not know how the phone is oriented, you have no way of figuring out which way the user is moving. Make sense? Very good. This makes orientation necessary. And what is 3D orientation? 3D orientation is essentially the plane's own reference frame is, let's say, X, Y, Z. Orientation is what rotation you need to give to the plane's own reference frame to align with the global reference frame, which is northeast vertical sky. Here's the example. The plane is in some orientation. That orientation is the plane's own XYZ or the IMU's own XYZ. We do not know that orientation. But suppose the plane rotates. You should look at this animation if you didn't see this, because my students spent a lot of time doing this. The plane rotates such that the plane's XYZ local, the plane's own or the plane's local XYZ axis aligns with northeast and vertical. Right? Suppose it had to rotate some 45 degrees on some axis. Then can you say the plane's orientation is 45 degrees around that axis? Right? Because whatever the plane is really pointing to, if you give that rotation to that plane, it will align with the northeast global reference frame, which is northeastern sky. So the 3D rotation needed to bring the local coordinate frame to the global coordinate frame can be called the plane's orientation. This is actually beautiful. Right? So if you know that 3D orientation, 3D rotation matrix, you are in business. So if your friend is giving you the IMU readout from the phone call, but if you somehow figure out what rotation you should give to his plane so that his plane is pointing north, the wings are pointing east, and the Z is pointing towards the sky. If you know that rotation matrix, then you're in business, because whatever data he's reading out, you can multiply it with that rotation matrix and you are in the global reference frame. Something to think about once after this lecture to make sure you have total clarity that orientation is rotation and rotation is a matrix. Therefore, orientation of a device is actually a matrix. Very good. So that's where we will stop today. And we'll pick up from this. And I really want you to think about why is orientation of a device with respect to the global reference frame a matrix. We'll stop here. Questions. The class ends over here, but I'll take questions.
If anyone has anything serious, go ahead. But I guess if no one has anything to say, I was wondering, why is it called music?
Oh, multi-user. Wait, give me a second. I'll just quickly Google. Multi-user signal. multiple signal classification.
I thought maybe it was like inspired by some kind of musical algorithm.
No. Okay. Multiple signal classification. Yeah. And classification class is basically AOA. I mean, that's the class. That's the classification you're doing. Yeah. Other questions?
I have a quick question about this IMU algorithm thing. So I was just wondering whether there is some research done on looking at this thing from a different angle, like maybe like machine learning, like training like a neural network or something.
Tons of research,
Okay.
Mohammed. Yeah,
so is there any like good results on that?
You know, there have been some reasonably good results of late, but all of that is with fusion, meaning that you take the LiDAR view of the self-driving car along with IMU and together they give good results. Or you take the camera view of your VR goggles and along with IMU, it gives good results. And it has also taken motion models into account, meaning, and we'll talk about this pretty well actually, meaning that, look, if you just try to do motion tracking with IMU, things will diverge over time. Right? Meaning, we'll talk about this, meaning your friend is telling you the IMU data, but over time, your estimate of where the plane is and where the true plane is will over time diverge. Why? Because the noise of those measurements, basically the errors that you have in estimating, there is no way of correcting the error because you never know the ground truth. So the error will keep accumulating. Okay. But then you can say something like, let's say you're doing it with your arm, with your wrist, and you're trying to measure where your wrist is from the IMU, and your estimate is diverging from the truth. But then at some point you can say, hey, my estimate of where the wrist is 3 feet away from the shoulder. How can that be? Right? Because I know that the length of the arm is at most 2 feet. Then you can say, my estimate must have diverged at some point. Let me correct it. Let me correct that back, that 3 feet to 2 feet. And these are the opportunities that you have to do corrections, meaning you're using domain knowledge, the knowledge that human arms are 2 feet at most, or the knowledge that when self-driving cars drive, their lower bound on velocity would be maybe 40 miles per hour and the upper bound is 80 miles per hour. They cannot travel at 200 miles per hour. So if at any point in your algorithm, you suddenly realize that your estimated velocity of the self-driving car is 100 miles per hour, you know that you should cut back. You made some mistakes and you should adjust everywhere. So these kind of domain knowledge, motion models, and other sensor information, you fuse them. And this is where sensor fusion becomes interesting. And we will talk about sensor fusion and algorithms for sensor fusion, such as hidden Markov models kind of things. And using those fusion, people try to rein in the errors of the IMU. Right? Mohammed, great question. And we'll talk about some of them and I'll give you pointers for more reading.
Thank you.
Other questions?
I know we are trying to look at this airplane mapping problem using IMU, but this particular problem can be more easily solved via GPS techniques, right?
Correct.
Like tracking the plane's path.
Yeah. If it is coarse-grained, then it can be solved by GPS. Okay. But imagine a drone doing that at the same location. GPS will give you the same location.
Right.
Right. But you need to know that movement. Right. For example, you know the major Boeing accidents that were happening,
The MCAS issue. Yeah. Right.
The angle of attack, right? Boeing, all these planes use gyroscopes, IMUs, to understand that kind of motion. Right? Planes have GPS, but they cannot rely on GPS for that kind of precision, right? So they actually have expensive GPUs, right? In fact, in the angle of attack, if you read about some of the post-mortem that has happened, the gyroscope was failing. And that is why the gyroscope was saying that the plane's nose was not that high. In fact, it was much higher. And that's where the crashes were happening. So in fact, there's some statistics which says that many of these drone crashes actually happen, 40% of those problems are actually because the IMU error or the IMU tracking error has failed. Somewhere it has diverged, and that's why it crashes. Okay? So GPS is much more coarse-grained, deep. IMUs are much more fine-grained, and it gives you all these degrees of freedom.
Got it.
Now, one thing you can do with GPS is, for a drone, you can put a GPS here and you can put a GPS here, right? You can put two GPSs and you can see how their locations are changing. From that, you might be able to infer orientation, right? But GPS does not give you that precision, right? Especially in a multipath kind of environment, it's going to be much worse, right? IMU does not care about any environment because it's internally, it measures orientation, rotation, and acceleration. And there's a lot of work around IMU GPS fusion. You do both, right? So in fact, when IMU is diverging, you can use GPS to reset. Other questions?
No question, Professor, but thanks. See you later.
Thank you very much. Okay. See ya. Bye.
Thank you.
Thanks.
Thank you.
Thanks.